Hello everyone. So far we have had much discussion about VLSI design. We have already learned about how we can implement the logic circuit in CMOS, how we can calculate the delay and the power. We have also learned about different circuit families that have been operational. So we have developed a basic idea about VLSI, and in this lecture and the lecture that will come in future, we would try to analyze what more we can do, what's the system, different type of systems that we can design using VLSI and CMOS technology. So in this lecture what we would do is we would take examples of some structural blocks, and we'll try to make them, we'll try to develop a logic around them, and we'll try to find the equation and the circuit how those structural blocks can be made. It will help us to solve real world problems when it comes to VLSI. Now the first problem that we will be dealing with is a parity generator. What is parity generator? Parity generator is a circuit which gives the output P is equal to 1 if there are even number of 1s as input, and output P is equal to 0 if there are odd numbers of 1 as input. That is even parity. P is equal to 1 means even parity. That is we see there is a black box here. We do not know the logic inside it, but these A0 to AN are the inputs, and if there are n plus 1 different inputs, if the number of ones in the each input can be 0 and 1. So if the number of ones in the input are even, then P will be equal to 1, and if the number of ones in the input are odd, then P will be equal to 0. Now before designing the parity generator, one thing we must take into consideration is that we see the number of inputs is AN. From A0 to N, that is there are n plus 1 inputs. Now the problem is that the value of n has not been stated. Since the value of n has not been stated, it can assume any value. That is, we have to make a generalized design which will work for any number of inputs. That is, we can make a logic block, and we can cascade this logic block in such a way that they work for any number of inputs. So here let us give an example what we want to do. We want to make this block. Each of the block will take input, and it will generate the parity Pi depending on the parity of the previous block. That is, if the previous the logic is similar to this, suppose a word contains 1010, this is a binary number. So we see there are two numbers, 1 and 1. Since 1 and 1 there are two ones, then Pi would be equal to 1 because this is even parity. Now let us observe that if the next bit here is 0, then it still remains even parity. If the next bit here is 1, then there are 3 ones and it becomes odd parity. Again, let us look for the example of odd parity. Here we have 3 ones available. That is, in this case our Pi is equal to 0. This is odd parity. Now if we introduce a 0 afterwards, it still remain odd parity, but if we introduce a 1 after this, then the number of ones would be 4, and then it will become even parity, and Pi would be equal to 1. From this discussion we can say that if any digit is equal to 1, then the parity which was there in the previous case will be changed. If A is equal to 1, the parity which was there in the previous case would be changed. If A is equal to 0, the parity which was there in the previous case will remain same, and it will not be changed. It can be stated, it can be explained in this way, that suppose we do not know how many inputs are there. So what we do is we make this generalized block. Suppose there are 3 inputs, that is, we have to check the parity of 3 bits. So here it goes A0, here it goes A1, here it goes A2. the parity output of this is the parity input of the second block, parity output of the second block is the parity input of the third block. This is the final parity. So this is how we can cascade similar blocks to get the desired output. The logic is the new parity will change from the old parity if A0 is equal to 1. New parity and the old parity will remain same if A0 is equal to 0. Now how can we design it? To design it, let us just assume a box. This box will do the work. Our input is A. Suppose this is input AI. This is the ith block. Suppose as our problem statement states, there are n plus 1 number of inputs. So there will be n plus 1 number of blocks. Of those blocks, the ith block is this. And here we have Pi minus 1. That is the parity generated from the previous block which was present here. And this is the Pi, the parity generated from this block, which will be going to the future blocks present in this direction. Now what we do is we can, now the logic is, if Ai is equal to 0, then parity Pi is equal to Pi minus 1, does not change. If Ai is equal to 0, what Pi and Pi minus 1 would be same. If Ai is equal to 1, then what happens is parity Pi becomes Pi minus 1. The parity is changed, that is, it would be Pi minus 1 bar. Why? Because there can only be two cases, Pi and Pi bar, because each of them are single digit binary numbers. So we can consider that we have true inputs available in true and complementary forms. That is, here we have Pi minus 1 generated, here we have Pi bar generated, and here we are providing input as Ai bar as well. Then the logic would be Pi is equal to Ai bar Pi minus 1 plus Ai Pi minus 1 whole bar. So logic is, if Ai is equal to 1, then the previous parity will be reversed, that is, we will find bar. If the present input Ai is equal to 0, then the previous parity will prevail. So this this over here is the logic block involved, logic circuitry or the logic expression that will be involved in this particular box. So how can we actually design it? We can design it by, we have true and complementary input. So what we can do is, we can see Ai bar P and Ai Pi minus 1 bar. So we can actually say that this is Ai Pi minus 1. The relation is XOR. So this XOR relation will give us the value of Pi. And if we add a NOT gate, we provide an XNOR relation, it will give Pi whole bar. So this is the logic circuitry that will be included in this box. And so these blocks will be repeated over and over and over again, and for each new digit that will be arriving, the parity will be updated. For example, let the first digit be 1. If the first digit is 1, then obviously Pi would be, initially there was no parity, that is, initially there was neither even or odd. So if the first input is 1, it will become odd parity and the output will be 0. If the next input is 1, then what will happen? A is equal to 1 and Pi is equal to 0. Since A is equal to 1, this will change. So we will get parity is equal to 1. If we include a new block, suppose now the input is 0, then what happens? We have 1 here and the input is 0, so parity bit will not change. So our output will remain 1. Let us see, in 110 we can see there are two ones, so the parity is 1, so this is true. Again in 11 there are two ones, so parity is 1, this is also true. In this there is a single one and parity is 0, that is true. If we cascade it further, let us include another block over here and provide 1 as input. We have 1 over here and we have 1 here, and from this expression we find that the pi would be reversed if ai is equal to 1. So if ai is equal to 1, this will be reversed and the output would be 0. And we can see that 1101, here the number of ones is 3, so the output is bound to be 0, or it is odd parity. This is how we can create a generalized parity generator. Please note that it is not n plus 1 bit parity generator. We have actually designed a single bit parity generator which can be cascaded as many times as we want, and we'll get the desired output accordingly. Next problem that we will be dealing with is bus arbitration logic. The block diagram is like this. If there are n inputs from A1 to AN, there are n outputs from A1P to ANP. Now the logic how this works is, this is our logic block. We have from AN to A1 and we have outputs from ANP to A1P. We have different outputs. Then the logic is, the higher the bus value, the higher the priority. That is, priority order increases from A1, A2, A3 to all the way up to AN. And if AN is equal to 1, ANP will be equal to 1. And all the other ANs, that is AN minus 1P, AN minus 2P dot 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 A1P, these all will be 0, irrespective of what the inputs AN minus 1, AN minus 2, AN minus 3 dot 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 1 A1 are. That is, the highest priority belongs to AN. If AN is equal to 1, that AN to the power P will be 1 irrespective of what other inputs are, and all the other outputs will be turned into 0. Now if AN minus 1 is equal to 1, then AN minus 1 P would be equal to 1, but in that case AN has to be equal to 0. If AN is equal to 0, then AN minus 1 P would be 1, with AN minus 1 becoming 1. This is because AN has a higher priority than AN minus 1. In this case, AN minus 2, AN minus 3 dot 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 A1. What these inputs are doesn't matter. AN to the ANP would be 0. All the other outputs would be 0. Only AN minus 1 P would be 1. So this is how the logic works. The priority rises from bottom to top, that is from A1 to all the way to AN, and the output at one point of time only one output is 1 and all the other outputs are 0. Now when we want to design this logic, again we can see that the number of inputs stated is AN, that is, the number of inputs has not been specified. So as a result, we have to design something which is generalized. We have to make a generalized design. Now let us just, since we want to make a generalized design, let us take a simple block which will take input as AI and output as AI to the power P. For the sake of calculation, we are assuming that AI has a priority somewhere between A1 and AN. So this is the logic. Now AI can make, if AI is equal to 1, it can make AIP is equal to 1 if and only if all the other higher priority bits are 0. That is, there is no higher priority that wants to assert itself. So we include another input which will come from another block, that is the previous block or the higher parity block, and we name is that Gn plus 1. This is called grant line. G is grant line. The logic of G being, if G is equal to 1, that means no other higher priorities have been asserted. That is, if G not Gn plus 1, Gi plus 1, if Gi plus 1 is equal to 1, it will indicate Gi plus 1, Gi plus 2, Gi plus 3 all the way to Gn, that is Ai plus 1, Ai plus 2, Ai plus 3 all the way to An are 0. And the output we are considering Gn. This output, logically speaking, this output would be equal to 0 if Ai is equal to 0. If Ai is equal to 1, this output will depend on this, because we are considering we have multiple blocks like this. Here we have Gn minus 1, I minus 1. Above we will have Gi plus 2, Ai plus 1, Ai plus 1p, Ai minus 1, here we have Ai minus 2. So this is the logic. The logic is different, the blocks are cascaded, and it is to be noted that this would be equal to 1 if none of the block in the upper segments have been asserted, that is none of the outputs of the upper segments are 1, and this would this will have to become 0 if any of the block has been asserted. Now the logic, how would we determine the logic? We can determine the logic. Our output depends on our input, and our output depends on if any of the logics in the previous case has been asserted or not. That is, our output will have a value, can have a value of 1 if Ai is equal to 1. So if Ai is equal to 1, then output Ai to the power p, Aip will be 1 if this is equal to 1. It will be 0 if this is equal to 0. So we can write Ai is equal to Gi plus 1. Why? We can see that if Gi plus 1 is 1, none of the higher priorities have been used up. That is, An is equal to 0, An minus 1 is equal to 0, An minus 2 is equal to 0, dot dot dot. Now we are considering Ai. All the higher priorities are 0. In that case, if the immediate if the higher priority is 0, grant line is equal to 1. If we have asserted Ai to the power p would be 1 if higher priorities are 0, and since higher priorities of 0 makes Gi plus grant line is equal to 1, so Ai would be equal to grant line. Now if the higher priorities are not 0, for example, let us suppose if Ai plus 1 is equal to 1, Ai plus 1p would also be equal to 1. In that case, what would happen is a higher priority has been asserted, so this G over here will become 0. If this G becomes 0, no matter if Ai is 1 or 0, this Ai will always be equal to Gi plus 1. So in this case it will be equal to 0. Even if Ai is equal to 1, Aip will be 0. Now if Ai is equal to 0, there is no question about it that Aip can never be equal to 1. It will always be equal to 0. Now this one output we have determined, and there is another output logic. What would happen to Gn? Again, in case of Gn, we see if Ai is equal to 1, If AI is equal to 1, then what happens? It happens, it will it has a capability of making this as 0. It has a capability of making this as 1. AIP can be 1 if GI is equal to 1. AIP can be 0 if GI is equal to 0. Now if AI is 1, GN will have to become 0 because priority has been asserted. All the lower priorities will be 0. If AI is equal to 0, GN will have to be 1 because no priority, this is a high priority term which hasn't been asserted, so the lower priority terms can be asserted. So GN can be termed as AIP bar when AI is equal to 1. Again, AIP is equal to GI plus 1. So we can write GN is equal to GI plus 1 bar. When is it true? This is true when AI is equal to 1. If AI is equal to 0, AI is equal to 0 means this thing hasn't been asserted. If this thing hasn't been asserted, GN will remain same as GI, not GN, my mistake. GI will remain same as GI plus 1. That is, if it was 0 here, it will remain 0. If it was 1 here, it will remain 1. So this is basically the logic that we'll be implementing. So inside the logic block, what will we have? We'll have two inputs. The logic of AIP would be AI GI plus 1. If AI is 0, then output is 0. So it would be AI GI plus 1. And the logic of GI would be AI GI plus 1 bar and plus AI bar GI plus 1. So if we implement a block which will have this logic, that block will serve our purpose. So the block, each of this block or each of the generalized block will contain input as AI and GI plus 1. If they are just passed through an AND gate, the output would be AIP, and after the AND gate if they are passed through an AND gate, output would be AIP. And what will happen if, suppose here the relation is A bar B plus AB bar. So if they are passed through an XOR gate, then we'll find GI here. So this is the block that will be operational here. This is how we can make an n-bit bus arbitrary logic. Now there is another input under consideration, another output under consideration, that is GN. So we have to determine what GN is. Now if AI is equal to 1, one thing is to be noted that AI once means this logic, this level, that is ith level, has exerted its that it wants to make the output 1. Irrespective of whether the output has already been exerted by a higher priority or not, AI is equal to 1 will indicate that either in this block output AIP has become equal to 1, or in the previous blocks output AI plus 1p or AI plus 2p or anything in the higher priority has become 1, because of which AIP has not become 1. So at any case, if AI is equal to 1, it will indicate that any of the priorities, be it ith level priority or I plus 1th level priority or I plus 2th level priority, those any one of those has been asserted. If any one of those has been asserted, then what will be the value of G? Our value of GI would be is equal to 0. This is because if G is equal to 1, no priorities have been asserted, Since ai is equal to 1 indicates that priority has been asserted either in the ith stage or at a higher stage, then it will exert gi is equal to 0. Now if ai is equal to 0, what happens? ai is equal to 0 indicates that priority has not been asserted by the ith stage, but it does not state that priority has been asserted in any higher stages, any stage higher than I, that is I plus 1 or I plus 2 or not. So this gi will be the same as that which was provided as the input of this block, that is gi would be gi plus 1. Why will that be gi plus 1? That will be gi plus 1 because if we notice that priority hasn't been asserted in this case. If priority has been asserted in a higher priority or higher stage, then gi would be gi plus 1 will automatically 0. That will make gi is equal to 0. If priority hasn't been asserted in the higher stages, priority hasn't been asserted in ith stage as well, at that case gi plus 1 was 1 and gi will also be 1. So this means that if ai is equal to 0, if gi is equal to, if we put gi is equal to gi or I plus 1, if a higher priority input has asserted its dominance, then the lower priority inputs will get the grant line as 0 and they will be inactive. If the higher priority has not asserted its dominant, the lower priority will get grant line as 1, and as a result the output will depend on their inputs. So the block that is operational here will have the expression based on this and this. So each of these blocks will have an input AIP, will have an input AI, and each of the block will also have an input gi plus 1, and the logic will be AI. The logic would be AIP is equal to AI gi plus 1. If AI is if AI is 0, AIP is 0. If AI is 1, then AIP is gi plus 1. And again similarly, gi would be AI bar gi plus 1. So here if we just put this to AND gate, we'll get AIP, and if we invert it and take the gi plus 1 and put this to AND gate, we'll get gi. So this is the logic block that will be operational inside the circuit. So this is actually this block, and this is how we make the bus arbitration logic. The third problem we have in our hand is designing a 4-to-1 mux. Designing a 4-to-1 mux is easy. The logic is that a 4-to-1 mux will have 4 inputs and 1 output, and the logic is that, let us see, the logic is that if the inputs are 0 and 0, if the select pins are 0 and 0, what it will provide z is equal to I0, map I0 with z. If select pins are 0 1, it will map I1 with the output. If select pins are 0 2, it will map I2 with the output, and if select pins are 1 1, then it will map I3 with the output. That is, if select based on the select pin, which input will be connected to the output, that will be determined. So if we want to write the expression, we can write it as if we want to write an expression, we can write it as z is equal to, when S1 and S0 both are 0, we have output is equal to I0. When S1 is 0, S0 is 1, we have output is equal to I1. When S1 is 1, S0 is, S1 is 1, S0 is 0, we have output is equal to I2. We have both S1 and S2 as 1, we have output is equal to I3. So this is very simple logic circuit. We have implemented similar logic circuit 2 to 1 marks in our Verilog and also in our DSCH class. So if we want to let us look at the stick diagram. If we want to execute this thing with NMOS, the NMOS switches, then this is actually I0, this is I1, this is I2, this is I3. So we see that in case of S0 bar and S0 bar and S1 bar, this I0 is connected and that is connected to Z. In case of S0 bar, S1 bar and S0, I1 is connected. Again S1 and S0 bar, I2 is connected and I3 is connected with S1 S0, and this is how everything is connected to Z and we get the output Z. Now if we want to build it in a CMOS logic, as we have already learned in CMOS transmission gates, we have already learned that the PMOS or the pull up side is opposite to the pull down side. So the pull down side over here is same as this. For I0 we have S1 bar and for I0 we have S1 bar and S0 bar. For I1 we have again S1 bar and S0. For I2 we have S1 S0 bar, and I3 we have S1 S3. Now if we look at the the pull-up network will just act oppositely. Everything will be inverted. That I0 will be for S1 and S0. We see I0 is selected for S1 and I0 is again selected for S0. I1 will be selected for S1 and S0 bar. Here we have I1, this is selected for S1 and this is selected for S0 bar. Similarly, I2 will be selected for S1 bar, S0. We have I2 here which is selected for S0 and S1 bar. And I3 will be selected for S1 bar, S0 bar. So here for S1 bar we have selected I3 and we have selected I3 for S0 bar. So this is transmission gate CMOS representation of the same mark circuit. Now the last design that we'll be looking is general two variable logic block. What two variable logic block does is it has two inputs, suppose A and B, and this logic block can perform the task of A plus B, A minus B. It can perform the task of NOR, inversion, XOR, everything, and the output we will receive, output is a single bit output. It will depend on which task we want it to perform. So if we look at it, our logic block is like that. Suppose we have over here is 16 to 1 marks, and the output here is Z. The input here are C3, C2, C1, C0, and here we have all different sorts of inputs. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. We have inputs from A0 to A15. Now the logic would be, say we have a truth table available here. If I'm assuming it, if the inputs are 0, 0, 0, 0, if C1, C2, C3, C4 all are 0, then what will happen is our A0 will be selected, and since the output here we can see will be 0, so we can ground A0. Again, if the input programming are 0, 0, 0, 1, it will make a NOR decision. So NOR is this. We are connecting this here in the A1, and we have two inputs A and B. So if it's like 0 0 0 1, then we'll get output Z is equal to A1, that is A nor B. We have seen the third logic is A B bar. So what we can do is A B inverted, they pass through AND gate, and that will pass this to A2. Similarly, following the truth table that we have here, we'll just insert this logic circuits and all of the inputs will be connected accordingly. If we take another example, suppose 1 1 1 1 will give the output is equal to 1, so we make A15 is connected to VDD. Again 1 1 1 0 will make the output A plus B, so A B going through an OR gate. So this is how all these blocks will be generated and connected from A0 to all the way up to A15, and the output would be a generalized output, and the result will depend on what is the output that we want, that we will be selecting using the select pin or the input programming pin. This is how a general logic block is created, and any logic can be implemented using this block. Here we have for simplicity we have used two input logic blocks. General logic blocks can be created for multiple 4, 8, 16, any inputs as we want. In the last part of structural design, we'll be learning about programmable logic array. Now we know that we have three fundamental gates, which are AND gate, OR gate, and NOT gate. Using AND gate, OR gate, and NOT gate, we can actually design any logic function as we want. So this principle is being used in programmable logic array. For example, if I zoom it a little bit, zoom it here a little bit, where it is, and we can see that here we have inputs A and NOT gate A bar, B bar, C bar, D bar, E bar. That is, this is 5 input logic. It can perform 5 input logic function, and it can give 4 outputs. Now it has lots of AND gates. Each of them are lots of AND gates and OR gates. How it does is, here we see this is though for the simplicity, each of the AND gate has one input here. Actually this is not one input, this is multiple input AND gate. Now what happens is, see, here we have connected this, the input of the AND gate is connected here, 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 and here. So this is A, this is B bar, this is D bar, this is E. So our P1 is equal to A, B bar, D bar, E. Similarly, if you look, P2 would be A bar, A bar, C bar, E. So P2 is equal to A bar, C bar, E. Similarly, these AND logic functions are performed, and several AND logic functions are then passed through OR logic functions. That is, our Z1 over here would be equal to P1 plus P3 plus P4 plus P5. So Z is equal to P1 plus P3 plus P4 plus P5. Now we know P1 is equal to this, P3 is equal to, we can see P3 is equal to A bar, B bar, C bar, D bar, E bar. So A bar, B bar, C bar, D bar, E bar. Our P4 is equal to BC. So P4 is equal to BC, and our P5 is equal to DE. So P5 is equal to DE. This P3, P4, P5 and P1 are passed through an OR gate, and will get output is equal to Z1. So we can very easily understand that using this type of programmable logic array, we can actually through this OR gates and AND gate structure, we can actually execute any logic functions. So this is a very easy and important method for developing a generalized solution developing a specific solution for multiple inputs and multiple outputs logic structures. So this is AND OR based logic array, because we have AND here, we have OR here. Again, we know we have our two universal gates, NOR gates and NAND gates, with which we can perform any kinds of logics. So we can also make these using universal gate, and that is called NOR based PLA. So we have AND or OR based PLA, and we have NOR based PLA. So the structure of all the PLAs are same. We have the inputs, which goes to an input register, and it goes into a product terms generation. Then what it does is it generates the sum terms and it gives output, and the product terms are also available there. Similarly, in NOR PLA also, in the first NOR plane we perform the product, in the second NOR plane we perform the sum and get the output. The structure is similar. One thing, the AND or PLA perform those using AND and OR gates, and the NOR PLA performs those using NOR gates. Now we are connecting these dots here, but actually how do these things work in an actual CMOS circuit? These things do not work that way. We need actual MOSFETs operating, and these can be found here. Let us look at it. See, each line is connected to VDD. That is, each column is connected to VDD, and each row is connected to VDD here, which provide the product terms, and each column is connected to VDD, which provide the sum terms, and the sum terms are actually our outputs. Now what happens is, the row we have A here and A bar here. This is A bar, this is A, this is B bar, this is B, this is C bar, this is C, this is D bar, this is D, this is Z bar, this is Z. So we have true and complementary inputs available, and what it does is, the portion we have a MOS, it connects or exerts that particular line. For example, this is the line, this particular line is for B, and this particular line is for D, and since these two are connected, the P8 would be equal to BD. Similarly, in the similar way, P7 would be, here it is C, here it is C bar, and here it is D bar, here we have E bar. So our P7 would be C bar, D bar, E bar. Similarly, using these MOS gates, all the logic functions or all the product terms are created. Then product terms are placed in series, and from there sum terms are created. For example, Z1 is equal to, here it is connected to P1, here P3, P4, P5. So Z1 is equal to P1 plus P3 plus P4 plus P5. Similarly, we have Z3, for example, is P4, P5, P7, P8. So our Z3 is equal to P4 plus P5 plus P7 plus P8. One thing is to be noted, that using PLA, thus we can see, using PLA we can perform or make any logic function known using the plus minus, using AND and OR gates. But one thing is to be remembered, that once we fabricate this PLA, it can perform only one logic operation that has been applied, or that has been designed using the MOS. That is, each PLA that we design will have 5 inputs, A, B, C, D, E, if designed in this way, and 4 outputs, A, B, Z1, Z2, Z3, Z4, and the operations they perform will have to be stated. That is, these MOSFETs have to be pulled, that is, these expressions have to be created at the time of building the layout. After the layout has been built and the IC has been designed, we cannot change this operation. That is, for example, P8 is equal to BD. In the future, if we want to make P8 is equal to BA, we cannot do this using this PLA. We have to design another PLA. that is PLA is not programmable on the go. This is programmable, but this can be programmed only once. If we want to program it over and over again, like we do in microcontrollers and stuff, the device that we use is FPGA, field programmable gate array. Using that FPGA, we can write a code, for example a Verilog code, and get the outputs accordingly. We can program it over and over again. But for PLA, we can program the PLA once, and it goes on to work like that for all the time to come. That's all for structural design. In the next lecture, we will be learning about some subsystem designs like arithmetic, logical unit, and others. Till then, if you have any queries, you can ask them in the discussion box. Thank you so much.